All right, folks, welcome back. We've got Evaluating Limits Analytically Part 2. But before we turn and burn on this bad boy, I just want to do a quick review of the discussion we've had about evaluating limits so far in terms of not what a limit is, but how we evaluate and find a limit. So we have three different techniques. The first is numerical, and that's looking at a table of values that get closer and closer as we get closer and closer and closer to the x value of interest. Another way to find a limit is to graphically to inspect the graph and see what the graph approaches as we get close to that x value of interest. And finally, we have the analytical techniques. And the difference between these three is that the analytical techniques give us an exact value of the limit. And those involve algebra, and they're often can be trickier than the other two. The analytical techniques we've talked about so far are direct substitution, where we just physically take that x value of interest and plug it into our function, see if we get an output. Then dividing out, so canceling out a common factor from both the numerator and denominator, and then rationalizing. If we have some irrational expression that causes us a problem, we can rationalize that expression, and that sometimes will take care of our issue. Last but not least, helpful theorems, and we're going to see an example of a helpful theorem today that we're going to use when those other three techniques don't work. Okay, so that's it. Let's now jump back into the notes. We're going to start with properties of limits. Over here on the left-hand side, I've got a list of kind of our initial conditions of how we're going to, just some criteria we're going to set up before we go in and discuss these different properties of limits. The first is that b and c, lowercase b and c, are real numbers. So anything you can point to on a number line, n will be a positive integer, 1, 2, 3, 4, 5, 6, etc. F and g are going to be functions that have the following limits. So the limit of f of x as x approaches c, where c is a real number and it's our value of interest. The limit of f of x as x approaches c is capital L. So capital L is the limit. Another function here, g, the limit of g of x as x approaches c is equal to k. So our limits for these two functions at the value of interest are capital L and capital K. Now let's take a look at these five different properties. The first is the scalar multiple property. And it says the limit of b times f of x as x approaches c is equal to b times L, where b is a real number that we talked about when we set up these properties. So one thing I think you'll notice about this property is it seems kind of obvious. If you take some number, some real number, and multiply it by a function, then the limit is just going to be that real number multiplied by the limit. So, and I think you'll see that with all five of these properties, they pretty much work like you would expect them to. For the next one here, sum or difference, I have a statement I'm going to write off in the margin that I think will help illustrate this. But we have the limit of f plus g as x approaches c is equal to the limit of f plus the limit of g. So I have a way that I'm going to say this to try and help you remember it. Okay, folks, so the way I like to think about this one is the limit of a sum, and here's our sum. So the limit of a sum is the sum of the limits, and that's that second part there when we're adding the two limits. And that kind of works for the rest of these properties too. For property 3, we have a product. So the limit of a product, f times g, is equal to the product of the limits, L times k. For property number 4, we have the quotient limit. The limit of a quotient, f divided by g, is equal to the quotient of the limits, L divided by k, as long as the limit k is not, the number k is not 0. And then last but not least, we have this power rule of limits, power property. It says the limit of f of x raised to the nth power as x approaches c is equal to that value L raised to the nth power. And again, I think these rules work kind of like you would expect them to work. So let's just jump into example 1 here and illustrate how these properties work. So in example 1, we're given the limit of f of x as x approaches c is equal to 3/2. the limit of g of x as x approaches c is equal to 1/3. And then we're asked for all sorts of different combinations of the functions f and g for limits of the combinations of those functions. Remember, in this example, we know nothing about f, we know nothing about g other than the limit at one specific x value, and that x value is c. Okay, folks, there's, again, simple example illustrating some of these properties of limits. In part A, I had the scalar multiple property. In part B, I had the sum difference property. Part C, I had the product property. And then here we had, in part D, we had the quotient property. And I know some of you might have been a little frightened here. I had to divide one fraction by another. Just remember that when you divide one fraction by another, you just multiply the numerator by the reciprocal of the denominator. Okay, let's move in here in example 2 and take a look at, see how else we can apply these properties. So this one, we're given the limit of f of x as x approaches c is equal to 64. So all we're told, again, we know nothing about the function f other than the limit as x approaches c, and that is equal to 54. So let's take a look here and see if we can't figure out the value of these limits using the properties from above. All right, folks, for example 2, here we have 4 more problems involving properties of limits, and I think some of you might be confused by something here, and I want to point this out because it's a contradiction with one of the properties I showed you above. So I rewrote this as the limit of f of x to the 1/3 power, because the 1/3 power is equivalent to the cube root. So if I go back up and look at my properties, I thought the integer had to be a positive integer. Or the exponent had to be a positive integer, and this is 1/3 is not a positive integer. It's positive, but it's not an integer. It's a rational number. Well, same thing shows up in part D here, where I had f of x to the 2/3 power. Seems like a contradiction, but I'm actually going to show you a property, an additional property later in the notes that says it's okay to do it this way. All right, let's move on and talk about the squeeze theorem. And I'm going to introduce the squeeze theorem by way of an example. And the example follows here, but I do want to make one quick comment. The squeeze theorem is an example of one of the helpful theorems that we can use to determine a limit after direct substitution, dividing out, and rationalizing don't work. Okay, so the squeeze theorem is something that it's not directly tested on the AP exam. You're not going to have to prove it, or you're not going to have to quote it as having been your justification for an answer. However, there are some limits that are a result of the squeeze theorem which you need to know. So I would call those consequences of the squeeze theorem that you need to know. So let's start this example. The first thing I'd like to do is apologize. You deserve better than this, folks. The numbering is all jacked up on this problem. It starts at 3, 4, 5. This example should be labeled 1, 2, and 3 because we have 3 steps. So again, you deserve better than that. I hope you can forgive me. So we're going to call that 1, 2, and 3. All right, so step 1 here says determine the following limits. So we've got the limit as x approaches 0 of the absolute value of x. Well, the absolute value of x is a continuous function. I can just use direct substitution there, and I know the value of that limit is 0. The next one is the limit of the opposite of the absolute value of x as x approaches 0. That function is also continuous. Direct substitution yields the limit of 0. Okay, step 2 here says graph the following functions on the same set of axes. So I'm going to graph h of x, which is the opposite of x, g of x, which is the absolute value of x, and then this crazy one here, x times the sine of 1 over x. I'm going to use my I'm going to get some help from my graphing calculator here, and then we can just kind of insert that image right here. So let's take a look and see what we can get from our TI Inspire. First thing I'm going to do is adjust these axes so they match the ones that we had in the notes page, just to kind of zoom in on on the important features we're going to be looking for in this graph. So that's going to go from an x value of -2 to +2. And this, we're going to go with the same on the y, -2 to +2. Okay, now I'll graph those two functions. There are my two absolute value functions, absolute value of x and opposite of the absolute value of x. Just going to hide those labels. Don't need to see those, they're not too helpful. So this graph's a little crazy. X times sine of 1 over x, if I could enter it correctly. X times sine of 1 over x, grip it and rip it. Holy cow, take a look at that, folks. That's a crazy graph. As I inspect that graph, it looks like it comes in, it hits that absolute value graph, absolute value of x graph, bounces down, and then bounces back up, and then it looks like there's some oscillation in there, and it comes out and does the same thing on the other side. So it'd be convenient if I could snap a picture of that and insert it in the notes so we could then discuss it. Well, would you look at that? There's the graph I just created in my TI Inspire. It's now in the notes page. That's pretty convenient. So the next thing we're going to do is look at step 3. It says make a conjecture about the limit of that function. We called it f. X times sine of 1 over x as x approaches 0. First of all, if we were to try to direct substitution here, we have 1 divided by x as the input to the sine function, and we know that's undefined. So this function is actually undefined at x equals 0, but again, that doesn't matter. We should still be able to find the limit as x approaches 0, assuming that it exists. So I'm just going to make some observations about the graph in this example. See if you agree. All right, folks, that's what I noticed. It appears that the graph of f is always kind of sandwiched or squeezed between the graphs of h and g. And since the limit of h of x as x approaches 0 is equal to the limit of g of x as x approaches 0, and those two limits equal 0, then the limit of that middle function, the one that's squeezed, x times sine of 1 over x, the limit of that function must also be 0 as x approaches 0. So folks, that is an example that illustrates the squeeze theorem. We're going to shut it down now and continue talking about the squeeze theorem in the next video.